We are living through a moment in human history that is, well, it's simultaneously miraculous and, if you really stop and think about it, deeply unsettling.
Mm.
I want you to picture a scenario. Imagine there's a nondescript metal box sitting on your desk, just a plain box.
Okay.
You can ask this box a question that the smartest human beings on Earth have been trying to answer for 50 years and failed. Maybe it's a biological mystery that could cure cancer, or maybe a complex prediction about a Supreme Court ruling.
And the box just hums for a second and spits out the answer.
Yeah.
Instantly.
Instantly.
And here's the kicker, right? The answer is correct. It works.
Yeah.
It cures the disease. It wins the lawsuit. It solves the problem.
Exactly. But then you look at the box and you ask, okay, that's amazing, but how? How did you do that? What's the underlying law of physics here? What was the specific legal reasoning?
And the box says nothing. Or, even if it could speak, the explanation would be so mathematically complex with millions of parameters and dimensions that no human brain could possibly comprehend it.
We're getting the what without the why.
Exactly. We are entering the era of what we might call the knowledge paradox.
Yeah.
We have the answers, but we are rapidly losing the explanations. We're sort of trading understanding for utility.
And that is precisely what we're unpacking today. We have a stack of 3 completely different sources that, when you layer them on top of one another, they tell this fascinating story about the future of truth. We're going to see how this exact same problem is playing out in 3 totally different arenas.
It's a story about geometry, philosophy, and the law. It sounds like a strange cocktail, I know. I don't think those 3 usually get invited to the same dinner party.
Huh.
But they are all grappling with this exact same black box problem.
Okay, so let's lay out the stack for today before we dive in. First, we're going to get into the weeds with some heavy-hitting theoretical computer science. We have a paper from the NeurIPS conference, that's, the big AI summit where all the cutting-edge stuff happens. The paper is titled Hardness of Learning Neural Networks Under the Manifold Hypothesis.
This is our foundation. It's asking a really fundamental question. Is there a mathematical limit to what AI can actually learn from the shape of data?
Yeah.
Or are we just assuming it can learn anything if we just throw enough compute at it?
Then we pivot to the philosophy of science. We've got a paper from the PhilSci archive called The Epistemology of AI-Driven Science, The Case of AlphaFold.
And this one hits hard.
It really does.
Yeah.
It asks, if an AI predicts a Nobel Prize-winning discovery but can't explain why, is it actually science?
That is a question that is keeping a lot of academics up at night right now.
I bet. And then finally, we take all that high-minded stuff and drag it, kicking and screaming, into the courtroom.
Right into the real world.
An article from the American Bar Association on using AI for predictive analytics in litigation. This is where the rubber meets the road. Using these black box predictions to win high-stakes cases. Real money, real people. So the mission today is to connect these dots. We want to know if we are, cheating by using knowledge we don't understand, or we just emptying dots on a graph we can't even see.
And if we are, does it matter? I mean, it forces us to redefine what we even mean by knowledge. Is knowledge something that has to live inside a human head, or is it just a system that functions reliably?
Okay, let's unpack this. We have to start with the math.
Always.
Because if the math doesn't hold up, the philosophy and the law, they don't matter. So this NeurIPS paper by Kiani, Kwang, and Weber, it deals with something called the manifold hypothesis. I hear this term thrown around in machine learning circles constantly. It sounds very sci-fi, very Star Trek, but what exactly is a manifold in this context?
To understand a manifold, you first have to understand the nightmare of high-dimensional space. And I really do mean a nightmare.
Okay.
Our brains are wired for 3 dimensions. Up, down, left, right, forward, back. Maybe time is a 4th if you're feeling spicy.
Right. I tap out at 3.
Well, imagine you have a high-resolution image, let's say. A standard picture of the cat you found on the internet. That image has, say, 1 million pixels.
Right.
In mathematical terms, that single image, it lives in a 1,000,000-dimensional space.
Explain that. How does a flat picture have 1 million dimensions?
Because every single pixel is a variable. Each one can change independently. So to describe that specific image mathematically, to plot it on a graph, you would need a coordinate system with 1 million axes.
Okay, my brain hurts already. So we have this 1,000,000-dimensional space, it's effectively infinite.
It is functionally infinite, yes. Now, imagine if you just randomized every single one of those 1,000,000 pixels. You just rolled a die for the color of every pixel. What would you get?
You'd get static, white noise. It's like an old TV with no signal.
Exactly. And that is what most of that massive million-dimensional space consists of just chaos,
Mm.
static, meaningless noise. But a picture of a cat isn't noise.
No, it has structure. It has ears, whiskers, fur, eyes.
Yep.
It follows rules.
So the cat picture is a very specific, very rare arrangement of pixels. It's a tiny island of meaning in this vast ocean of noise. And that is the manifold hypothesis. It's the idea that real-world data-like photos of cats or recordings of human speech or legal documents, it doesn't just exist randomly in that massive, chaotic space.
It's not scattered everywhere?
No. Instead, all that meaningful data lies on a much lower dimensional structure hidden inside that space. And that structure, that's the manifold.
Right. I've heard the analogy of a crumpled sheet of paper used here.
That is absolutely the best way to visualize it. So imagine a massive empty 3D room. That room is your high-dimensional space. It represents all the possible static and noise.
Okay, I'm with you.
Now, take a flat sheet of paper. That's a 2D object, right? You can draw a line on it. You can navigate it easily. It has structure.
Simple enough.
Now, twist that paper, crumple it into a ball, fold it over itself, and just throw it into the middle of the room.
So the data points, let's say they're ants living on that paper, they still think they're on a 2D surface. They can just walk from one corner to the other.
That's it.
But to us, looking at the whole room, it looks like this complex, knotted 3D thing.
Exactly. The ants, the data points, they're confined to the paper. You will never, ever find an ant floating in the empty air of the room.
Okay.
And the assumption in AI research for a long time has been, hey, if the data actually lies on this simple, low-dimensional manifold, this twisted paper, then learning should be easy.
It feels intuitive. You just need the neural network to find the paper, smooth it out, and ignore all the empty air in the room. Less chaos, more structure.
Right. It's the cure for the curse of dimensionality. It explains why AI works at all. It's not learning the whole room, it's just learning the shape of the paper.
Yeah, there's a but.
There's a huge but.
Yeah.
This NeuroIPS paper comes in and says, not so fast.
Well.
Kiani, Wang, and Weber are effectively the wet blanket on this optimism.
A reality check.
Big one. They ask a critical question. Does simply knowing that the geometry exists, knowing there's a sheet of paper somewhere in the room, does that actually guarantee that an AI can learn the function on it efficiently?
And their answer is no.
A resounding no.
So they introduce some specific geometric concepts to prove this. We need to talk about reach and curvature. Curvature seems straightforward enough. How much does the paper bend?
Yes, curvature is how sharp the turns are. If your crumpled paper has really sharp creases, like origami, it's hard to navigate. If you're driving a car on the manifold and the road makes a 90-degree turn instantly, you're going to crash.
And neural networks don't like crashing.
They don't. But reach is the really fascinating one. Reach is a measure of global smoothness. It effectively asks, how far can you step away from the manifold into the empty space before you get confused about which part of the manifold is closest to you?
Okay, that's a bit abstract. Can we get an analogy for reach that sticks?
Yeah, let's try this. Think of a river. The river is your manifold. Now imagine this river winds back and forth in a tight S shape. If you're standing on the bank and the river bends back comfortably, you know exactly which bank you're on. You're on the north bank or the south bank.
Okay, simple enough. I'm standing on the grass, looking at the water.
But now imagine the river loops back so tightly, a hairpin turn, that the two sections of water are separated by a tiny strip of land, maybe just a foot wide.
So the river has almost doubled back on itself.
Exactly. Now, if you stand in the very middle of that narrow strip of land, and you close your eyes, and I ask you, which part of the river is closest to you?
I wouldn't know. It would be equally close on my left and on my right. The distinction just blurs.
And that point where the ambiguity starts is called the medial axis, the distance from the manifold to that axis. That is the reach.
So high reach is good. The river loops are wide and lazy. Low reach is bad.
Very bad. Low reach means it's tangling back on itself tightly. The algorithm gets confused about which loop of the data it's even looking at.
So the paper argues that even if you have bounded curvature, no sharp creases, and you know the reach, you can still have a shape that is impossible to learn.
Correct. They identify what they call a hard regime, and this is where the math gets really, really trippy. They construct a space-filling manifold.
A space-filling manifold? That sounds like a contradiction in terms. I thought a manifold was supposed to be simple, like a line or a sheet. How can it fill space?
Imagine a thread, a simple 1D line. Just a standard piece of string. But this thread twists and turns so chaotically and so densely that it passes through almost every single quadrant of a high-dimensional cube, a hypercube.
Like a ball of yarn that's been compressed into a solid brick.
That's a great visual for it. Technically, it's still a single thread. It has a start and an end. You could trace it. But functionally, it occupies the whole volume.
Wow.
The authors use something called gray codes to construct this. It's a way of counting in binary where you only change one bit at a time. They prove that you can create a manifold that follows all the geometric rules. It has bounded curvature. It's smooth.
But it's a nightmare.
It's a complete nightmare. It acts like a chaotic mess. It wraps around exponentially many quadrants. So if a neural network is trying to learn a function on that thread, it's impossible. Because 2 points that are physically right next to each other in the room might be miles apart if you followed the thread.
So the geometry alone doesn't save you.
Not at all. If the manifold fills the space, knowing it's a manifold provides zero advantage. It's exponentially hard to learn. You're right back to the curse of dimensionality. The whole assumption that the manifold makes things simple, it just turns out to be false in this regime.
But clearly, AI does work. We see it recognizing faces, translating languages, driving cars. So we must not be in that hard regime all the time.
And that is the good news. The paper also defines a learnable regime. They find that learning is possible if the manifold is efficiently sampleable.
Meaning?
Essentially, if the volume of the manifold doesn't explode as you add more dimensions, if it behaves itself.
And this is where they talk about interpolation, right? This seems key to understanding how current AI actually works.
It's everything. If the manifold is well-behaved, think of a nice, clean sphere, you can cover it with a reasonable number of sample points. The paper calls this an epsilon net.
So you just sprinkle a bunch of known data points all over the shape.
Exactly. And if you have enough samples covering the shape, the neural network essentially just plays connect the dots.
Yeah.
It interpolates between the points it knows to guess the points it doesn't.
So successful AI isn't necessarily understanding the deep logic of the universe.
Yeah.
It's just connecting dots on a shape that happens to be well-behaved.
That's the core implication. It is high-dimensional interpolation. But here's the kicker. The authors didn't just want to do theory. They wanted to see where the real world fits. Is a picture of a t-shirt a simple sphere, or is it a chaotic ball of yarn?
Right.
So they tested this on real data sets, images of handwritten digits, the famous MNIST dataset, and photos of clothing, which is called Fashion MNIST. They used diffusion models to estimate the intrinsic dimension.
And what's the verdict? Is a t-shirt simple or complex?
It's messy. It turns out real-world data is heterogeneous. The intrinsic dimension varies widely.
No, it's not one clean number.
Not at all. A picture of a 1 might be geometrically simple. It's basically just a line. But a picture of a complex plaid shirt, that can be geometrically messy. It has folds, shadows, texture.
So we're somewhere in the middle, the heterogeneous regime, as they call it.
Exactly. Real life isn't a perfect sphere, but it's not a space-filling nightmare curve either. It's a mix. And this math tells us that our ability to learn depends entirely on that geometry. When the geometry gets too complex, the black box just stops working. It hits a hard limit.
Okay, so that sets the stage mathematically. We have these systems that work by interpolating data on complex shapes. But when they work, they really work. And that brings us to our second source, which deals with the fallout of that success.
The black box dilemma.
We are pivoting to the PhilSci archive paper by Daria Zakharova, and we're talking about AlphaFold. This is the perfect example because it bridges that gap between connecting dots and winning Nobel Prizes.
It really is the defining case study for modern science. For anyone who doesn't follow molecular biology, you have to understand the scale of this problem. For 50 years, biology had a grand challenge, the protein folding problem.
Give us the I'm 5 on that. Why is protein folding so hard?
Okay, so your body is built of proteins. Proteins are basically long strings of amino acids. Imagine a beaded necklace.
Right.
We know the sequence of the beads. That's the 1D information. We can read that from DNA very easily. But a protein doesn't work as a loose necklace. The second it's made, it instantly folds up into a complex, knotted 3D structure. And the shape determines the function.
Like a key fits a lock.
Exactly, like a key fits a lock. If it folds one way, it's an enzyme that digests your food. If it folds another way, it's a deadly prion that destroys your brain. Same beads, different fold.
And predicting that fold is hard because of physics.
Because of the insane number of interactions. Every single atom pushes and pulls on every other atom. To simulate that using pure physics, a supercomputer would take, literally, years to simulate the folding of just one small protein. It was considered basically impossible to solve computationally.
And then DeepMind comes along with AlphaFold.
And they just cracked it.
Oh.
AlphaFold predicted over 200 million protein structures. That is nearly all the proteins known to nature. Demis Hassabis and John Jumper won the Nobel Prize for this just recently. It's arguably the biggest scientific breakthrough of the century.
But, and this is a huge but, which is why we have this philosophy paper, AlphaFold didn't give us a new law of physics. It didn't say, here's the equation for folding. It didn't explain the mechanism.
No.
It just said, here's the answer.
Precisely. It is opaque. It doesn't provide a theory. It doesn't explain why the protein folds that way. It just gives you the structure. And this creates what the paper's author, Zakharova, calls an epistemological trilemma.
I love a good trilemma. This is where you have three statements that all sound true, but logically they can't all be true at the same time. You have to pick two and throw one out.
That's it. So let's break them down.
Let's do it.
Okay, here's claim number 1. AlphaFold produces scientific knowledge.
That feels true. Scientists use it every single day. They design drugs based on its predictions. It works. It feels like science.
Right. Now, claim number 2. Predictions alone are not knowledge unless they are derived from known theories or laws.
This is the traditional view of science, right? You need to show your work. You have to explain why something happens for it to be science. Otherwise, it's just a lucky guess or a correlation. This is the Newton standard. Newton didn't just predict where the apple would fall. He gave us the theory of gravity.
Exactly. And now, claim number 3. Scientific knowledge cannot be strongly opaque. Meaning, if no human being on Earth can understand how the result was derived, if it's totally inaccessible to the human mind, can we really call it science? Can you know something if you can't explain it?
Ah, I see the conflict. If we accept claim 1, that AlphaFold is knowledge, we have to throw out either claim 2 or claim 3. We have to admit that either we don't need theories anymore, or that science can be something no human understands.
And Zakharova uses this brilliant thought experiment here to highlight just how weird this is. She calls it the science guru.
The oracle on the mountain? I love this.
Imagine there's a person, a guru, who sits on a mountain. You go to them and you ask, will this chemical cure cancer? And the guru says, yes. And they're right, every single time. They just predict Nobel-worthy discoveries, one after another.
Okay.
But when you ask them how they know, they just smile and say nothing. Or maybe they speak in a language no one understands.
Would we give the guru the Nobel Prize?
Zakharova argues, probably not. We would treat their predictions as useful bets, maybe. We'd say, hey, go ask the guru, he's usually right. But we wouldn't say the guru has scientific knowledge.
He'd say they have a magic trick. Or intuition. We wouldn't publish the guru's yes in a physics journal.
Of course not. But with AlphaFold, Hassabis and Jumper did get the Nobel Prize. And scientists are treating the outputs as knowledge. In some cases, they aren't even double-checking the predictions with experiments anymore. They just download the structure and start working.
So we're treating the AI better than we would treat the guru. We've decided that the predictions are the knowledge, regardless of the explanation.
That is the crux of the crisis.
So how does the paper resolve this? Which claim do we toss out?
The author argues we have to reject claim 3. We have to accept that scientific knowledge does not require a human mind to understand the why.
Wow. That is a massive shift. That changes the definition of science from understanding the world to just predicting the world.
It moves us to a position called functionalism. It draws on the philosophy of a guy named Alexander Bird. The idea is that knowledge is social. It's a structural thing, not a mental state.
So it's not about, I understand this, it's about the system works.
Exactly. It rejects internalism, the idea that knowledge must be inside your head. It embraces externalism. Think about it. When you use a calculator to divide, say, 4,592 by 37, you don't perform the long division in your head.
No.
You don't verify every step of the circuit board logic. You just trust the output.
Because the calculator is reliable.
Right. If the tool is reliable, if it's trustworthy, and if it's integrated into the workflow of science, the truth filtering process, then it functions as knowledge.
So if the community trusts it, and it produces results that let us build bridges or cure diseases, it is knowledge, even if it's a total black box.
Trust becomes more important than understanding. We are moving from being the generators of answers to being the validators of systems.
That's profound. It sounds like we're kind of resigning ourselves to being the junior partners in the relationship. The AI does the heavy cognitive lifting. We just sign the checks and make sure the machine is plugged in.
Or, to put a more positive spin on it, we're becoming the architects. We build the system, we verify its reliability, but we don't need to check every single calculation. We trust the interpolation.
Right.
We trust that the manifold the AI found is the real one.
Okay, so that's biology and philosophy. We've accepted the black box there because, well, it cures diseases. But surely when we get to something as human as the law, we demand more than black box answers, right?
You'd think.
I mean, we need justice to be explainable. If a judge sends you to jail, you want to know why. You don't want a black box verdict.
You would think so. You would hope so. But our third source suggests, well, otherwise. This article from the American Bar Association shows that the legal world is sliding into this functionalist approach just as fast as the biologists are.
We're talking about predictive analytics in litigation, and this isn't science fiction. This is happening in law firms right now.
Right. There's an old saying in law, if you can't know the law, know the judge.
Which usually meant, take the judge out for golf or ask around about their personality. Oh, Judge Smith hates it when you chew gum in court. Or Judge Smith is grumpy before lunch.
Exactly. It was a hunch. It was soft skills. It was gossip. But now, it's hard data. We have AI tools analyzing massive data sets, past rulings, filings, docket entries, case outcomes, to quantify judicial behavior down to a percentage point.
Okay, so the article has this example, right, with Judge Smith. Can you walk us through that? Because that's what made it click for me.
Yeah, this is where it gets really, well, practical. So you're a lawyer. You get a case, a complex contract dispute.
Okay.
And it lands on Judge Smith's desk. You run Judge Smith's name through the AI analytics platform. You don't ask your colleagues, you ask the database.
And the black box spits out a pattern.
The AI tells you. Judge Smith favors plaintiffs when contract terms are ambiguous, but he favors defendants when the terms are clear. And, crucially, he grants summary judgments 20% more often than the district average.
And a summary judgment is basically a quick ruling without a full trial, right?
Exactly. It ends the case early. So you have this insight. It's not based on reading Judge Smith's diary. It's based on finding the shape of his past decisions, his own personal manifold. So what do?
You pivot your entire strategy.
Immediately. You stop arguing about fairness or equity or what's right.
Right.
You focus entirely on clarifying the contract terms to trigger that defendant favor bias, and you file for summary judgment immediately. You're optimizing for the algorithm of the judge.
You're hacking the judge.
You are. And notice what's missing. You don't know why Judge Smith rules that way. Maybe he hates ambiguity because he's a strict textualist. Maybe he just wants to get home early for dinner, so he likes summary judgments.
He flips a coin.
Maybe. Doesn't matter. You have the pattern, and you exploit it.
This connects directly back to the space filling curve from the math paper. The judge's behavior is a complex, high-dimensional manifold, and the AI finds the shape.
And it connects perfectly to the philosophy paper. The lawyer is a functionalist. They don't need to understand the judge's internal psychology. They just need the reliable output to win the case. If the tool says, file for summary judgment, and you win, that tool provided knowledge.
There was another example about settlement versus trial that felt even more, robotic. This is where the AI basically becomes the client's financial advisor.
This is where the AI becomes the decision maker. Take an employment discrimination case. The client comes to you and asks, should I settle now or should I roll the dice and go to court?
In the old days, the lawyer would say, well, I have a good feeling about this, but juries are unpredictable. It's really up to you.
Now, the AI says, based on 5,000 similar cases in this jurisdiction, you have a 60% chance of winning a trial with a payout between $100K and $300K. But you have a 70% chance of a settlement between $80K and $150K.
It turns justice into an expected value calculation. It's Moneyball for court.
And the client looks at those numbers, 60% versus 70%, and chooses the settlement. The AI's probability score effectively decided the outcome of the dispute. The human lawyer didn't weigh the moral scales. The algorithm weighed the statistical scales.
That is just wild. The AI didn't assess the moral merit of the discrimination claim. It didn't look at the evidence in a human sense. It just looked at the statistics of similar cases. It interpolated the manifold of employment discrimination outcomes.
And the ABA article warns lawyers about this. They say you have to verify the data sources. Is it state data? Federal data? Because if the data is wrong, the manifold is wrong, and your strategy collapses.
But if the data is right...
It's hard to argue with a 70% probability.
It validates that philosophical argument perfectly.
Yeah.
The lawyer is using applied opaque knowledge.
Yes. They are betting their client's future on a system they can't fully explain because the system is statistically reliable. They are trusting the reach of the data.
So, okay, let's try and connect all these dots. We've got the math, the philosophy, the courtroom. How do they all fit together?
I think.
Right.
Well, I think the math is the foundation, right?
Yeah.
It tells us when this can even happen.
That this opaque knowledge is only possible if the data has a certain shape.
Exactly. If it lives on a learnable manifold. If the world is too chaotic, If it's that space-filling curve we talked about, the AI fails.
Right. If Judge Smith is truly random, or if the protein folding physics were truly chaotic with no structure, AlphaFold would fail.
It would. But where the world does have structure, the AI finds it by connecting the dots via interpolation. It finds the hidden paper in the room.
And the philosophy tells us that when this happens, we have to accept a new kind of truth. We have the what without the how.
Strongly opaque knowledge.
Yeah.
We are accepting answers that we cannot verify with our own logic only by seeing if they work.
And the practice, the law, the biology, it shows us that we are already there. We've already accepted the trade. We voted with our feet. We use AlphaFold because we want the drugs. We use the litigation analytics because we want to win the case.
We have become functionalists. We have implicitly decided that solving the problem is more important than understanding the solution. We've sort of fired the philosopher and hired the engineer.
Which brings us back to that shift in the human role. You mentioned we are becoming validators.
I think that's the key takeaway. In the past, the human expert was the generator of answers. The lawyer came up with the strategy from scratch. The biologist figured out the folding mechanism using first principles.
Right.
Now, the human expert is the validator. We check the inputs, we sanity check the outputs. But the actual cognitive work, the pattern recognition, that's being outsourced to the manifold.
It's a humbling thought. We are the managers of intelligence, not the source of it. We're the ones keeping the server room cool.
And it raises the stakes on that verification. Because if the black box hallucinates, or if the manifold is actually a mess and the AI is just guessing, we might not have the intuition to catch it anymore. If we lose the why, we lose the ability to know when the what is wrong.
Okay, here's where it gets really interesting for me, and this is my final provocative thought for you to chew on. I want to go back to that space-filling curve from the NeurIPS paper.
The chaotic thread that acts like a solid brick. The hard regime.
Right. The paper says that if the geometry is that complex, AI can't learn it, hits a hard limit. The interpolation just fails.
Yes.
So what if huge chunks of our reality are that complex? What if the why of protein folding or the why of human justice is actually a space-filling curve? What if the reason we couldn't find the simple law of physics for proteins for 50 years is because there isn't a simple one? What if the reason laws are messy is because human conflict is messy?
That is a disturbing thought. It implies that the AI isn't finding a hidden, simple truth. It's just finding a good enough approximation on a chaotic mess. It's finding a shortcut that works 99% of the time, but misses the deep reality.
Exactly. And if that's true, we are entering a world where we trust a non-human intelligence to guide our most critical decisions, from curing cancer to sending people to jail, based on correlations that don't actually reflect the deep reality. We are navigating by a map that works, but it doesn't actually match the territory.
We're surfing the manifold, just hoping the wave doesn't break. We're walking on a tightrope over the empty room, trusting the math holds up.
So are we comfortable with knowledge that is permanently decoupled from human understanding? That is the question you need to ask yourself the next time an algorithm tells you what to do.
And if you figure out the answer, let us know.
Thanks for listening to The Deep Dive.